Okay, so let's start with a quick recap of where we were at after last class. So everything yesterday was about SL3, but basically building up this structure theory associated with SL3. Okay, heading towards this this fundamental theorem called the theorem of highest weight. So we talked about the root diagram of SL3. I haven't put it right here, but I'll draw it shortly, as well as the fundamental weights. And yeah, so I guess let's just go through the statements of the theorem of the highest weight for SL3. So for SL3, every irreducible representation is the direct sum of its weight spaces. This is the analog for general irreducible representations to the root space decomposition. Okay, so you're decomposing with respect to the action of this Cartan subalgebra, these diagonal matrices. Okay, so implicit in this formulation here is that a Cartan subalgebra has been chosen. Okay, so there's a choice there. Okay, so then we get weight spaces from that choice. Second statement is every irrep has a unique highest weight, and it is dominant integral. Okay, highest, we introduced this partial ordering that was induced from our second choice, namely that second choice being the choice of simple roots. Okay. And so from that, we have this notion of highest, meaning that for any other weight in the representation, it's lower or equal to this highest one. That's not the same thing as a maximal element or weight. Okay, so maximal element says there's no other weights in the representation that are above the given weight. Okay. Seems very similar, but it's not, because with a partial order, you can have two elements that are not comparable. Okay, but being highest does actually say that everything else, all the other weights are comparable with this one, and mu is the highest one. Okay, so just be careful about that. Two irreps with the same highest weight are isomorphic. And lastly, well, the second condition says that mu being a highest weight is dominant integral. Dominant integral pictorially means that it's in this fundamental Weyl chamber. But conversely, given any dominant integral weights, there does exist an irrep with that highest weight. Okay. So it's a very, very clean statement that, well, summarizing, SL3 irreps modulo isomorphism are classified by highest weights. Okay, writing it out in terms of the in terms of the fundamental weights, you put these coefficients over the nodes of the Dynkin diagram, and these coefficients have to satisfy this dominant integral condition. Okay, so integers, integer valued, and in fact, non-negative integer valued. Okay. A couple of reminders about some of the ingredients in the formulation. So this Cartan matrix is very important. It's so it's evaluating this pairing between the simple roots and the corresponding co-roots, okay, with respect to this pairing coming from the killing form. And we computed this so to be 2 minus 1 minus 1, 2. Okay. The fundamental weights are an alternative basis to the simple roots defined by this condition. Okay, pairing with the co-roots, you get a Kronecker delta. Okay, and we introduce these because they're more well adapted to talking about general representations, as you saw from the statement of the theorem of highest weight. Okay, where did this dominant integral condition come from? It really comes from SL2 theory. Okay, SL2s are, we have several SL2s embedded into SL3 naturally. And in particular, for any positive roots, we have an SL2 triple, okay? A Y, H, and X in the notation that we were using from SL2 theory. And so you could take a choice of root vector and a choice of root vector over here as your raising and lowering operators. And then you could define an H out of this, okay? So you take the co-roots for alpha, and then you sharp it. Okay, you convert it from a covector back to a vector. Okay, it turns out if you this co-roots construction is exactly useful in this case because it gives you an H inside an SL2 triple. Okay.
This E alpha, so they define it.
Yeah, so that these by definition are root spaces. So, sorry, root vectors.
Okay, yeah.
Okay, but that's a good point because there is always ambiguity of rescaling within that eigenspace, right? But the claim here, and there is something to be proved here, that you could always find appropriate eigenvectors here to make an SL2 triple. Okay, so that's something that needs to be proven. Yeah, so that pins down some of this rescaling freedom. Okay. So it can always be chosen. Most importantly, for now, at the moment, as far as where this condition comes from, we have an H. Okay. So from SL2 theory, you know what the weights, when these H's act on representations, there's very tight conditions. Namely, you have to have integral conditions. Okay, so the weights have to be all integral. The highest weight has to be non-negative integral. Okay. So writing this out, this highest weight out in this fundamental weight basis, first of all, we could extract these coefficients by just pairing this with the corresponding co-roots, simple co-roots. Okay. And these are the M's that we were using before as highest weights in the SL2 theory. So you automatically, from that theory, get non-negative integrality. Okay. So this is dominant integral. So here's the fundamental Weyl chamber. Okay. So anything here is a non-negative linear combination of lambda 1 and lambda 2. But then if you want it to be integral, it has to lie on this lattice. That's the weight lattice. Okay, that's where all the action is happening. Okay, so here are the weight diagrams that we saw yesterday for the standard, dual standard, and adjoint reps. Okay, and I've gone ahead and drawn the walls of the fundamental Weyl chamber here. Okay, in each one. So you can see that the highest weight is in this fundamental Weyl chamber. Okay. There are various differences. I mean, notice that in this standard representation case, this fundamental weight here lies on one of the walls. Okay. And notice that the number of weights in that representation are, in a sense, smaller. There's only 3 of them here. Similarly, this lies in a wall. There's only 3 weights appearing here. Here, there's something in the interior of the fundamental Weyl chamber. Here, there's more weights appearing, and that's no coincidence. Okay, we'll see this. There's a natural symmetry group acting, and the orbits of this symmetry group, this is called the Weyl group. These orbits degenerate on the wall. Okay, but you have larger orbits going through elements in the open chamber. Okay. Okay. Sorry. Let me just. Okay, so I thought we could start by just using this theorem of highest weight for an example. Okay, so I'm going to start with this example being the standard representation. You take the wedge 2 of it. Okay, so let's recall the weights for the standard representation. Okay, so the weights here were epsilon 1, which is lambda 1, epsilon 2, which is minus lambda 1 plus lambda 2, and epsilon 3, which is minus lambda 2. Okay, so if I'm taking the wedge 2, I am taking skew-symmetric tensor products here. And so the dimension will be 3 choose 2, which is also 3 in this case. Okay, so dimension of this guy, that's right, is 3 choose 2, which is 3. The weights, when you take tensor products, right, how do the weights for the factors give new weights? You have to take sums. But since I'm doing a skew-symmetric tensor product, I have to take unordered sums. Okay, as opposed to with a symmetric product, you take, you could have repetition as well. Okay, unordered sums without repetition. Unordered sums without repetition. Okay. Of the C3 weights. Okay. So this means, for instance, epsilon1 plus epsilon2, epsilon2, what did I do next? Epsilon1 plus epsilon3, and epsilon2 plus epsilon3. Okay, I don't do epsilon1 plus epsilon1, right? Because if I take the wedge product of two vectors with itself, then I get 0. Okay, weight vectors are always non-zero. Okay, so I have the weights written over here, and so I just start pairwise adding them up. And I get lambda2 for the first one, lambda1 minus lambda2 for the second one, and minus lambda1 for the third one. Okay. This list you've seen before. We actually just saw it, right? It's actually this list. Okay. This is the dual standard representation. Okay. So yeah. So let me write some stuff down. So each of these eigenvalues, right, has like whenever you have an eigenvalue, you have an eigenspace at least of dimension 1. Okay, and we know, so there's one here, at least one here, at least one here, at least one here, but the whole thing is 3-dimensional, so these are exactly 1-dimensional. So each has multiplicity 1, and these are the same weights as for the dual standard representation. Okay, so by theorem of highest weights, we can conclude that these representations are isomorphic. Okay, remember the notion of isomorphism, you have an intertwiner between these representations. Okay, the action of the Lie algebra on both settings can be mimicked, can be mapped one to the other. Okay, so of course, not just as vector spaces, as representations. Okay. So that's of course using this this big canon, this theorem of highest weight. Okay, but it's like just looking at this discrete data behind it, you're getting this isomorphism. Okay, we can exhibit this isomorphism more concretely here. Okay, so if we take the usual bases, okay, so standard basis for C3, let's take the dual or C3 dual. Then similar to what we had when we were considering the SL2 case with C2 and C2 dual, there's a volume form here. Okay, so rather so what I mean, so I'm going to take these covectors, take a completely skew symmetric tensor product. Okay, so what does that mean? I take all possible permutations of this, so E1, E2, E3, E1, E3, E2, etc. There's 6 of them. Okay, and then I add them up, but I add them up with a sign in front, depending on the odd or evenness of the permutation. Okay, so that's a skew symmetric tensor product. Okay, analogous to what would happen for taking this a wedge product of 2 elements. Okay, so this guy, similar to the SL2 case, is SL3C invariant. Okay, it's natural with respect to this SL3 action. Okay, so then in terms of this invariant tensor, you can exhibit what this isomorphism looks like. Okay, namely, so wedge 2 C3 is spanned by simple wedge products like this. Okay, spanned by that, so I just need to define this linear map, this intertwiner on basic elements, simple elements like this. Okay, so what am I going to send it to? I take V wedge W, and I'm going to insert these vectors into this into this volume form, into this invariant tensor. I'm going to take V, shove it into the first slot, and then take W, shove it into the second slot, or the other way around, doesn't matter. And I'm going to leave the third slot open. Okay, so this now becomes a linear form on C3, as in it's an element, it's a functional. So it's an element of C3 dual. Okay. So this is a natural map defined by an invariant tensor. So therefore, this is going to be, an intertwiner. Okay, you can check that. Okay, so then that is an intertwine. Okay, so exercise. Questions? Second example is just to give you a feel for how you want to construct these more complicated representations, but we're still going to do it in a familiar setting. Okay, so we've seen that this is the adjoint representation. Okay, lambda 1 plus lambda 2 is the highest weight. But rather, I want to construct this as a sub-representation. Okay, sub-representation where? Okay, so first we'll do a recall. So lambda 1 is the highest weight for C3. Okay, and so you have these guys as, when we just saw this, those are your highest weights. Sorry, this, for the first one is your highest weight. C3 dual, you have the corresponding covectors. And you have, well, you have the negatives of, so you have the original basis, you have the corresponding dual basis, you have the weights. The weights for these guys just are the negatives of the weights of these guys. Okay, so. And right, so which one is your highest weight? So the highest weight is this one. Okay, here the highest weight is this one. Okay, these are the only dominant integral weights. Okay, remember, highest weights have to be dominant integral. Okay, so you could ask, when I take a tensor product, okay, what is going to be a highest weight there? Well, it's just going to be the tensor product of the two highest weight vectors. Okay, so then E1 tensor E3 is highest weight vector, highest weight vector. So inside the tensor product. Okay. With weights lambda 1 plus lambda 2. Okay. So therefore, so what we have is you have this highest weight vector, and then you could generate a representation from it, right? It's highest, so if I hit it with any of the raising operators, okay, coming from the positive roots, of course, it's going to kill it because it's a highest weight vector. So I could start letting the rest of the Lie algebra act, namely the lowering operators. That's going to generate a representation. Okay, the smallest subspace generated, that's G invariant, is going to be a sub-representation. Okay, so sitting inside here. Okay, this is C3 dual. Okay, and so we know the tensor product action. okay, induced from the action on the factors. So you could work out an actual sub-representation as you were doing in the SL2 theory. Okay. Just for concreteness now, of course, we know what this C3 tensor C3 dual is. It's another way of talking about endomorphisms, okay, just linear transformations. Okay. Okay. So, and just, yeah, to emphasize the identification here, EI tensor E J being the EJ being a covector. So this corresponds in this identification here to the matrix with a 1 in the IJ position and zeros elsewhere. Okay. And in this picture, of course, the action of SL3 is just via the matrix commutator. Okay. So therefore, in that identification, okay, this guy has highest weight vector E13. Okay.
Quick question.
Yep.
So when you say this V with the double line on the
Yep.
left side,
Yep.
you still mean these expressions of the polynomial and this
No. So when we're talking about polynomials, that's those are realizations for the high for these irreducible representations of SL2.
Yeah.
Okay. Now we're in SL3 land. Yeah. So when I write V and then subscript mu, that from the theorem of highest weight, it is some irreducible representation. Okay, but we haven't constructed it. That's what I'm doing now. Like, so this symbol can be treated as an abstract symbol
it's
that
from the existence.
it's from the existence theorem.
Okay.
But what I'm doing right now is actually showing you how to construct it.
Yes.
Okay. Yeah. So I'm constructing it in terms of tensor products of things that you know. Okay, namely this you know, this you know. So let's start taking tensor products. Okay, we get some space that we know, and then we're going to find this. We're going to realize this inside this concrete space as a sub-representation. Yep. Let's not get into no. I mean, we're in a vector space setting, and we have a Lie algebra, which is yeah. So
if we need the volume form, like invariant volume form in general, should be local compact.
No. Let's not get complicated. So it's an invariant tensor, right? And you have this action. You know what invariant tensor means under the action of a Lie algebra, namely that it's annihilated under that action. Yeah. Yeah.
This remember me creation and equation operator in quantum mechanics.
Yep.
But there is no higher states in the if you apply the creation operator many times, you still obtain new states. Less probably, but you're obtaining that they exist.
So here we're working with finite dimensional representations.
Oh.
Yeah, we're always in this entire course, we're working basically with finite dimensional representation. So there is going to be a highest one. Yeah. No, that's a very good point. There are good settings where you want to talk about infinite dimensional representations, but let's keep things manageable here. Okay, so here's a highest weight vector. Then we can start hitting it, right, with the action. Okay, so we want to apply lowering operators. So we know what lowering operators in SL2 language look like, and we picture them as moving to the left. Okay, but here we're in a plane, and what do the lowering operators look like? So apply to E13 the lowering operators. Okay, so what are your Y's? They are E21 and E32. These are the simple lowering operators. Okay, let's put simple. In the sense that these, this is root vector for minus alpha 1, and similarly for minus alpha 2. Okay. You could give me a Y3 corresponding to E31, root vector from minus alpha 1 minus alpha 2, but you don't actually need to. Why? Because it turns out when I take the bracket of these two, it generates that y3. Okay, so it's going to be sufficient to just apply these simple lowering operators to that highest one. Okay, so okay. So here's the result of what happens when you do that. Okay. So this is just a list in a tree of possibilities. And sometimes you get repetitions, right? So E31 is appearing there and there and there. Okay. But you just want to take the span of all of them. Okay. Until you get, until you get nothing new anymore when you keep applying these simple lowering operators. Okay. So just these in 3x3 matrix land. Okay, that's what this looks like. So all the non-trivial stuff is below the diagonal. Okay. And I guess this, this is the red one. This is the orange one. Okay. Okay, so so that's how you could generate this representation sitting inside a bigger representation. Okay, and so more. Okay, so but when you do this, what you're going to find is that, well, of course, yeah, you shouldn't expect it to fill out the entire representation, right? So this is 9-dimensional, and we know this is 8-dimensional. Okay, so there is a complementary subrepresentation there. We know that there is a complementary one because of this complete reducibility property. So we'll get where this W is a copy of SL3C itself, okay, as a representation of SL3. So this is our copy of this lambda 1 plus lambda 2 representation. What is this? What is a representative complement here? So you have trace-free matrices sitting inside all matrices, all 3x3 matrices. What is a basis? What can you take as a basis for this trivial factor here? It's just going to be the identity element, right? Because when I let an element from SL3 act on the identity element via the matrix commutator, you always get 0. Okay, so that clearly generates a trivial factor. Here's a story more abstractly, okay, in terms of weights. So this is the weight diagram. We started here, okay, with corresponding, I've put this into the root diagram, but this is really, it shouldn't be in this diagram particularly. So just this is this vector is corresponding to this weight, okay. The root vectors, okay, the simple root vectors were this one. Okay, this is minus alpha 1, and then I don't know why that shifted over. Minus alpha 2. Okay, so those are your lowering operatives. Okay, so you start out here, apply the matrix commutator with E21. Okay, then you're going to get over here. Keep doing that. Okay. When you go here, so do minus alpha 1 and then minus alpha 2, and then in the opposite order, it turns out you get different things. Okay, so these processes are not going to commute. Okay, and that's okay in this case because that's generating these two weight 0 vectors, which are going to span the Cartan subalgebra. Okay, then you keep going, generate some new vectors, until, well, at this stage at the bottom, you apply those lowering operators, you just get 0, so you get nothing new. Okay. Any questions about that?
Yeah, do you mind going over one more time why E13 is actually the highest wave
Yeah,
vector?
sure. So start out with how, like, where does this representation sit? Okay, we're building it up. It's inside this tensor product of the standard and dual standard. We know what the weight vectors and the weights are, and in particular, which ones are the highest one. E1 is the highest. Okay.
Find that they are the highest. You just
We had right. So we calculated the weights of this earlier. Those were the epsilons, right? Then we introduced this notion of partial order. Okay. And so yeah, we know, for instance, that epsilon 1 is greater than or equal to epsilon 2 because what are you supposed to do? You take the difference. And this is when you write out in terms of the simple root basis, it has non-negative coefficients. Okay, so this one is clearly the weights are corresponding. The corresponding weights are, this one is higher than that one, and this one is higher than that one. Okay, and here I've just written it out in lambda language. Okay, so this is the highest in this representation. These weights are the negatives of these weights. So if this is going to be the highest, its negative is going to be low, right? This is the lowest over here. Its negative is going to be high. Okay, so this is highest. Now I take the tensor product. Inside the tensor product, well, I start taking tensors of between these guys and these guys. But then the highest is just you take the highest from here and the highest from there, take the tensor product. The weight is going to add.
Okay.
Yep.
Then when you get to the root diagram, before we had that, we had the definition that when we subtract them, we need positive coefficients. So we have the greater than sign. Do you mind going down to the root diagram?
Yeah, sure. So
then if you look there, the coefficient of lambda 2 is 2.
Yep.
And the coefficient, and that doesn't matter at all.
I think you're confused. Yeah, because there are two bases here. So we could write this diagram. So this is the weight diagram for SL3. Okay. It's in fact coinciding with the root diagram, right? But just distinguish between the Lie algebra and the vector space that's being acted upon. In this case, they're the same, but it's just they serve different roles. Okay, and the this non-negativity condition that you're talking about is in terms of the alphas. Okay, so if I were to write the alphas out, this is good exercise. Okay, so let's do it. So alpha 1 plus alpha 2 is over here. This one is alpha 2. This one is alpha 1. This one is, I've already labeled it minus alpha 1, minus alpha 2 over here, and then minus alpha 1 minus alpha 2. So the coefficients there with respect to the simple root basis are all either non-negative or non-positive.
Yeah.
Okay. Yeah. Yeah. Good. Okay. So a similar strategy. Okay, so a similar is used to construct V A lambda 1 plus B lambda 2, i.e., we're going to realize it as a highest weight subrepresentation sitting inside where? Well, I take A copies of V lambda 1, I tensor them all together. I take B copies of V lambda 2, and I tensor them together. Okay. Of course, this is only going to make sense if A and B are non-negative integers, which they are. Okay. So from theorem of highest weight, we have A and B non-negative. So this is a reasonable construction. Okay, same strategy as we just saw. Okay, so what would be a highest weight over here? So here, your highest weight vector v, so v would be e1 tensored e1, so a times, and e3 tensored with e3 b times. Okay, so you tensor them all together. Just as a small remark here, I mean, this element is actually the same thing as if I took the 8th symmetric power of E1, okay? And this is the same as if I took the bth symmetric power of E3. So actually, this is sitting in something even smaller inside here. I could take the symmetric tensor power, the 8th symmetric tensor power of V lambda 1, the bth symmetric power of V lambda 2, tensor them together, and this would lie inside there. Okay. Okay, so that's how you construct these representations concretely from these fundamental representations. Yep, good.
Is this because, oh no, I don't know. Why can you do the symmetric? Is it because like the
Well,
ordering of these, when you look at the standard, the geo, then the ordering of each of them doesn't really matter?
just symmetrizing amongst the first and symmetrizing amongst the last, not overall symmetrizing.
Well, not overall.
No.
Okay.
Yeah. So I mean, the symmetric power of a vector with itself is the same thing as the tensor power. Okay. Okay, so that's how you construct these representations. Just take a pause.
Directly related, but there is some.
Okay, so I want to tell you about a nice group sitting in the background of what we've been doing. Okay, namely something called the Weyl group. Okay, so let me give you the definition. So let G be SL3 or SLn+1C. And then inside the Lie algebra, we'll have our Cartan subalgebra consisting of diagonal trace-free matrices. Okay, so with this choice, there are natural subgroups. So you could ask for the subgroup preserving this choice. That's the normalizer. Okay, so the normalizer of this given H is this N, sometimes written NG of H. So those elements of G that under the action on the Lie algebra, namely the adjoint action, if you let that act on H, then it should stay in H. Actually, because these are invertible elements, this inclusion is going to be an equality whenever that's true. The normalizer. There's also the center of G. So this is the elements, sorry, the centralizer. Yeah, centralizer. The centralizer of H. Are those elements of G that preserve each element of the Cartan subalgebra? Okay, so the normalizer acts on H, and it might shuffle things around inside H, okay, non-trivially. The centralizer fixes every point of H. Okay. So verify both are subgroups. Oh God, writing is getting worse and worse. Are both are subgroups of G. And Z is a normal subgroup of N. Okay, so if I take anything from N and I conjugate an element of Z, it'll stay in Z. Okay, so Z is sitting inside N. Okay. Z is sitting inside N. It's a normal subgroup. Okay. Normal subgroups, just in case your group theory background, you haven't played around much with those. Those are precisely the subgroups for which it makes sense to take a quotient. Okay, and that's this fundamental object that we're going to be talking about, this Weyl group. So the Weyl group of G is the quotient group W. Okay. And again, just in case you haven't played around with quotient groups much, let's just think about a simple example. Okay, not in this Lie theory context, but just talk about a clock. Okay, so a clock is basically like the hour ticks on the clock. You're basically working Z mod 12. Okay, so think of the group on the top as being the integers and the bottom as being 12 times the integers. Okay, so the bottom would consist of 0, 12, 24, et cetera, and they're negatives. And then we're considering this quotient. So we have equivalence classes. Okay, so 0 in this quotient actually means the equivalence class 0, 12, 24, all multiples of 12. 1 means all of those shifted by 1, et cetera, et cetera. Okay, and in the same way, we're thinking about this quotient of groups. Okay, so as sets, okay, there's that analogy, but in this case, you could actually have a multiplication on that quotient, and that's this quotient group structure. Okay, so let me just get a little bit further along with this to tell you how it comes up. Oh, the Weyl group? No, in general not. But in this example, yes, right? Because the Z is abelian.
Yes.
But for this one, no.
Yeah. So it is left quotient or right quotient?
We're going to consider left cosets. Yeah. Okay, but I'll make this very concrete later on. Okay, so so note that Z acts trivially on H. And we're going to get a W action on H. Okay, how is this defined? Okay, so on one of these diagonal elements, I'm going to define it as, well, just via this adjoint action. Okay, where W is A, and then we write mod Z. Okay, just like with this clock example. Okay, modular arithmetic here. we'll just use this analogous notion mod Z, as in we don't really care what's happening here. In making a definition via quotient groups, so I have a W, okay, which is A mod Z, and I'm using A here in the definition of the action, okay? When you do this, you always have to be careful that this is actually well-defined, okay? So an exercise here is that this is well-defined because Z, well, actually we already know, because Z acts trivially on H, okay? So it doesn't matter what this is. Okay, and again, what do I mean by mod Z? So I'm considering W to be like something in this equivalence class. So you could think of this as, you could take a representing element in the group to be A times some small z, where Z is in Z. Okay. So these guys act the same way, independent of what this little z is. Okay. Okay, so this is going to be well defined. So we're going to get a representation. We're going to get a representation phi of this W on GL of H. Okay. So here, yeah, one thing about this representation is that it has trivial kernel. So if you have a W that is in the kernel and acts just trivially, then this W has to have, well, A being in Z. Those are the things that act trivially. Okay. But W is A mod Z. So therefore, W is just the identity element in W. So what this is saying is that this representation phi, this map, has trivial kernel. Okay, it's an inclusion. So therefore, phi is injective, and so I could identify W with its image. Okay, there's no information lost there. Okay, so therefore, identify W with its image. So therefore, we can regard W as a subgroup of H. Okay. That's good. Okay, so we have this group acting on H, but of course, what we were doing up to yesterday and beginning of today, we're working in H star. Okay, but we know how to do that. If we have an action on a vector space, we can induce the action on the dual vector space. So induce the W action on H star as usual. So V of lambda is defined to be lambda precompose with this W inverse. So we have a group, a new group, acting on all the objects that we've been considering in this in this H star setting. Okay, so you can think of this Weyl group as being canonically associated with this choice of H, right? There were two choices that I said that were lurking in the background. This choice of H, this choice of simple roots. And the Weyl group is associated with this choice of H. So I'm going to prove one more proposition, and then we'll take a break afterwards. Okay, so the utility of this is it's going to act as a permutation group, a symmetry group on the set of weights. Okay, so in all those diagrams, there is a group acting. on the set of all weights. Okay, so let's take a representation of this group. And let's take little pi, the representation at the Lie algebra level. So the statement here is that the set of weights of IV is W invariant. Okay, so W is acting as a permutation group. It's permuting these weights. Moreover, the dimension of one of these eigenspaces, this geometric multiplicity, is constant along orbits of this group. Okay. So same geometric multiplicity. Okay, so this is a short proof. Let's have a look at it. Let's take non-zero elements in a weight space. And then let's take a W. Okay. So V is starting in this initial weight space. Okay, so where does AV lie? Okay. Well, the claim is that this is also going to be a weight vector. And to show that, we need to look at the action of H on it. Okay, so short computation here. So take AV, let H act on it. I'm going to slip an A inverse that doesn't change it. Okay, I'm going to rearrange the brackets. Okay, the parentheses, rather, so that I get this adjoint action coming in over here. Okay, so this is the same thing as A add A inverse of H. I guess I'll let that act on V. Just like that. Okay. But this A and A inverse are in the normalizer. So this will lie in H. Okay. I guess before that, I guess this is the definition of this element here. Okay. This lies in H. So when I have something from H acting on a weight vector, it acts via just a scaling. Okay, a scaling by what? Well, this vector lives in this weight space with weight lambda. So I have to take this input, put it into the functional, and then get a number. Okay, so this is a number. It's a number, and then I have this A acting. So this number, well, this acts linearly, so this number I could pull out front. And here I have lambda composed with W inverse. So that's the definition of W of lambda. So we take that covector, let it act on H, and that is a number, and it acts on AV. So therefore,
Where does the lambda come from?
here.
Yeah, but
Yep.
yeah,
So this is an element of H, right? This is a weight vector. By definition, being a weight vector says that elements of H act by a scaling by which number you take lambda and then you evaluate it on the input. Okay, so it's yeah, definition of what a weight vector is. Yeah, it's just the notation is a little bit heavier, but yeah, just think this is an element of H. Okay, so I shove that element into the functional, I get a number. Yeah.
And in the last expression, the W
Here?
lambda is the functional.
This is the functional,
Star.
yeah, which is the same thing as lambda W inverse.
Yeah.
Okay, and I'm evaluating it on H. Okay, so now this is a number. Okay, so yes, we're almost done. So we've just shown that this AV is a weight vector. Okay, it's a weight vector for which weight? W lambda. Okay, this is non-zero because A is right, A is a group element, it's acting invertibly. So we started out with V being non-zero, so this is non-zero. And so we've just completed the first statement. But moreover, the second statement about the multiplicity being the same. So the last claim follows since pi of A is invertible. Okay. So we have a group to play around with is the moral here. Okay. So of course this is abstract definitions and nice property that I highlighted. So how do you actually make this very concrete? That's what's going to be in the next lecture, and it's very pretty stuff. So basically, this Weyl group is a discrete reflection group. So we'll see how to articulate that in these weight diagrams and play around with it and really use it as a fundamental tool. Okay, so let me just give you a quick recap of where we were at with getting the Weyl group set up. So given a choice of Cartan subalgebra, so diagonal matrices, say, sitting inside SL3 or SLn+1, we define W as the quotient of the normalizer of H mod the centralizer of H, okay, n mod Z. So this is a quotient group, okay? And this acts on H, so this is an element from frac H, by the adjoint action. Okay, and even though there's a mod Z, this is well defined. Z acts trivially on H. And so we saw in the last lecture that we can identify, so we have an action on H, and this is in fact injective. Okay, this you have a map that's injective, trivial kernel. So we can identify W with its image. So therefore, W can be viewed as a subgroup of the invertible linear transformations on H. Okay, once we have one of these, then you could view it dually as acting on H star. Okay, and then we ended off last time with the nice property that W acts on the set of weights of any representation of G. Okay, so it's a symmetry group. It permutes the set of weights. Here, I'm going to give you a different point of view, which is really lovely. So here, W is viewed as sitting inside general linear transformations. Okay, but we actually could say even more than this. Okay, so I'm going to talk about the Weyl group as a discrete reflection group. Okay. So we know that the killing form B is invariant. It has strong invariance properties. Okay, so there's one exercise that says that this is aught G invariant. Okay, so aught G, automorphism group of G, is a subgroup of GL of G. consisting of those linear transformations that are invertible and preserve the bracket. So recall that, well, if I have the big adjoint action, okay, acting on GL of G, so this preserves the bracket, okay? So add G is sitting inside automorphisms, okay? But B is invariant under all automorphisms. So therefore, B is G invariant, okay? Or add G invariant, but it's like G is acting via the add representation here. So B is G invariant. Okay, B is a bilinear form on frac G, and all of that geometry on the space of roots and everything came from not the full B, okay, but it's rather its restriction to H. Okay, so we considered the restriction of B to H, and well, B being G invariant will tell you that this guy is W invariant. Okay. And similarly, for the pairing on H star. In other words, W is acting as orthogonal transformations. So W is sitting inside orthogonal transformations of H star. It's preserving this pairing on that space. Okay, of course, this is up until this point from when we gave the definition of W. This is still very abstract. We want a more concrete description of it. Okay, so let's start defining some familiar types of transformations, some orthogonal transformations, reflections, okay, in this setting. So given a root, okay, we're going to define the reflection S alpha. And here, yeah, we could either do it on H star, or even let's even be more specific here, to the real form, because that's where all the action is, right? So it's the reflection, so S alpha is this reflection in the wall, namely the perpendicular to alpha. By the following formula. Okay, so this is the same type of formula that you see in usual Euclidean geometry. Okay. And we'll just check that it has the properties that we expect from a reflection. Okay, but actually before I write that down, notice that we have this combination that we've seen several times before, namely 2 alpha divided by alpha alpha. Okay, so this is that co-root coming into play here. So I could rewrite this formula as lambda minus, and you pair lambda with alpha check, multiplied by alpha. Okay. So if you're a little bit rusty on this formula, let's just double check that it satisfies the right conditions, right? So we have alpha and then the perpendicular to alpha, so alpha perp. If I take lambda lying on this perpendicular, what is this doing? Well, it's doing nothing, right? This is 0. On the other hand, so you should have this picture that, okay, so you have, say, alpha perp, and you have alpha, okay? So what is it going to do to alpha? Okay, so if I have alpha in over here, then this cancels with that, and so I have alpha minus 2 alpha. So that's minus alpha. Okay, so what the reflection just did is it sends alpha to its, that's supposed to be a straight line. It sends alpha to minus alpha. Okay, but it fixes every point in this perpendicular. Okay, that's what reflection does. Okay, so reflection. Well, okay, so let's be concrete in the case of SL3 here. Okay, where do these come up? Okay, so for SL3, let's recall that alpha 1 is epsilon 1 minus epsilon 2, and epsilon 2 is, sorry, alpha 2 is epsilon 2 minus epsilon 3. Okay, so we're going to build a table here of certain choice of A sitting inside invertible 3x3 matrices. Okay, so here's a 3x3 matrix. So 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, swapping second, and this is, yeah, a swap between the second and third basis elements. Second column is its effect. So via the adjoint action on an H. Which H? Okay, it's the one we're usually using. That one. Next, we'll look at the effect of W, which is A mod Z. Okay, so first of all, on epsilon 1, epsilon 2, epsilon 3, and next on alpha 1 and alpha 2. And lastly, running out of space, but last column is what that reflection is. Okay, so when you take this element and then you let it act on the diagonal, a matrix looking like this, okay, so you conjugate using this element, then what that is going to do is it swaps the entries, the second and first entries. Okay. So, okay, so it swaps those entries. So what is it doing to the corresponding functionals that act on this? So it's going to swap these functionals. Okay. Right, so there is a step here, right? You have to induce the action on going from here to here. You have to induce the action on the dual space, okay? But it's not too hard to see that you will just get that swap on the first two basic functionals. What is the effect on these guys? Well, we just induce it. Okay, so we're going to get minus alpha 1 for the first one. For alpha 2, that will in fact be sent to alpha 1 plus alpha 2. And what we're getting is the reflection in alpha 1. Okay, and there are a few more. Sorry. Let me see. I want this. Okay. Yeah, because this part here has determinant -1. So I want to put a -1 here so that the overall determinant is +1. So that I'm SL, big SL 3. Okay. You have similar effects for these other ones. Okay, so I'll just quickly write up this table. Here you're doing a swap in 2, 3. Okay, so similar sort of results. And lastly, sigma 1, 3. Yeah. Okay, so here I'm swapping the first and the third. Okay, and what is the effect over here? Alpha 1 gets sent to minus alpha 2. This gets sent to minus alpha 1. Okay, here it's in fact a reflection in alpha 1 plus alpha 2 perp. Okay, so so what's the conclusion from this table is that these reflections, so this reflection in alpha 1 perp, that's called S alpha 1. Okay, so that transformation, this transformation, and this transformation, these are all elements of this W. Okay. So you have these reflections sitting inside there, and so therefore the subgroup, the subgroup generated by, oops, that's not it. Sigma 2, 3. Yep. Yeah, swapping 2, 3. Yeah.
But what does a -1 do then?
Why is there a -1?
Yeah, wouldn't that make H1 fine?
No, because I'm conjugating. So I have it
Okay.
in the front and then in the back with the inverse.
Yeah.
Yeah. Yeah, so it's not going to do anything to this H1. Okay, so I have 3 specific elements, but then we could talk about the subgroup generated by that. That's still going to stay inside W. Okay. And subgroup generated by these is in W. Okay. So here's a picture of what's happening. Okay. So here's yeah, sure. So here are weights of the adjoint representation, or also called the roots of the adjoint representation. And you can see the effect of these reflections, right? This set of weights is invariant under all these reflections. So if I take alpha 1, say, and I reflect it in this alpha 2 perp wall, so I'm applying S alpha 2 to it, then this gets sent to that, this gets sent to that, this gets sent to that. Okay. And you do similar reflections with the other, with respect to the other walls. So, right, you have a nice invariance property here. Okay. So I'm gonna move some stuff around. Oop. Okay, let's try doing like this. Sure. Right. So we had some definition up here with like you're choosing some sort of element A, okay, here from this normalizer. Okay. And you get a corresponding W in the quotient group. Okay. And it's acting on frac H. Okay. So that's what we've done over here. I've taken an A, a particular type of A that I'm claiming it sends one of these diagonal elements to another diagonal element. Okay, so I've induced what that is. Okay. Now from that action on H, you get the dual action. Okay, so a little computation. You do the, precomposite, you take a covector, you precompose by the inverse. Okay, so you get this effect on this. Okay. but we're using alpha language. So what is the effect on alpha on this basis, alpha 1, alpha 2, and it's this. And if you work it out, then you'll find that this is exactly the reflection alpha 1 through the wall alpha 1 perp. Okay, so there's again a little computation here. Okay, but actually we could just let's see, alpha 1, alpha 2 gets sent to minus alpha 1 plus alpha 2. So let's see, alpha 1 gets sent to minus alpha 1. Alpha 2 gets sent to minus alpha 1 minus alpha 2. So did I write a mistake? Alpha 1 perp. Where's alpha 1 perp? Sorry, I think that's a mistake. Yes, I think that's a mistake. Sorry about that. And there are potentially other mistakes here then. Alpha 1. Alpha 2. Ah, no. Okay, no, that was not a mistake. Try it again. Okay, let's try it again. Alpha 1, sorry, alpha 2 is this one. Alpha 2 in the alpha 1 perp, the mirror there, it gets sent over there. Okay, I think yeah. Okay. So similarly with the other ones. Okay. So let's start talking about this as a permutation group. Okay, so remark. So abstractly, what we're going to do is we're going to identify sigma 1, 2, sigma 2, 3, sigma 1, 3 with the corresponding transpositions. Okay. In the symmetric group. Okay, this is abstractly. Okay. You can think of these as acting on those positions in the diagonal matrix. Okay, this swaps the first two, this swaps the last two, this swaps the first and the third. Okay, so the symmetric group S3. Okay, this is the permutation group on 3 symbols. So I'll try to use a different letter just because it's S4. Okay, so there's this funky Gothic S. Okay. So the identity 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. These are the elements. Okay. Here elements are read left to right. So if I read this, 1 goes to 2, and it's in a cycle notation. So 1 goes to 2, 2 goes to 1. Okay. Similarly for this and this. What does this mean? It means permute. So 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay. You read it left to right. Multiplication of elements is given by composition, okay, written functionally. Okay, so let's see, interpret left to right. Okay, multiplication is written functionally. Okay, so for example, so 1, 3, 2, 1, 2, 3 is what? Okay, so let's just see. So let's start with 1. So I'm going to read the action, like do this first and then this. So this guy, this says, well, it's going to swap 2 and 3, but it's going to fix 1. So this does nothing to 1. So, and then it was followed up by this guy, which does what to 1? It sends it to 3. So I'm going to start this off as 1. 1 goes to 3. What does 3 get sent to? 3 here gets sent to 2. Then you follow it up by this transformation. 2 goes to 1. So therefore 3 will go to 1. So that closes up. What does 2 do? Well, it has to be fixed, right? So let's just check that. 2 goes to 3, and then 3 goes to 2. So 2 is fixed. Okay, so that's how you multiply. Okay, so little exercise. If you're a little rusty with permutations. Okay, so write. Oh, sorry. Let's see. Let's try to. One fact about the symmetric group is that it's generated by simple transpositions. In fact, S3 is generated by so-called simple. Whoa. Why do I have that? Simple transpositions. 1, 2, and 2, 3. Okay, so every element, all of these elements can be written as products involving these guys. Okay, so exercise. Do this first, then done. Okay. So just check the that 1, 3 is the right answer there. Okay. But this next fact that everything's generated by simple transpositions. So write 1, 3, 1, 2, 3, 1, 3, 2 as a product of simple transpositions. Okay, so we saw earlier that basically S3, which is the subgroup generated by those S alpha 1, S alpha 2, and S alpha 1 plus alpha 2. Okay, so this is contained in the Weyl group. But in fact, we have, so I'm not going to prove this, but you could see a proof in Hall. Okay, certainly for the SL3 case, but I'll state it for SL n plus 1. Here we have W equal to the permutation group on n letters, n symbols. Okay. So that fills up everything. It's so W is S3 in the case of SL3. Okay. So this Weyl group is an important group. It's an example of a discrete reflection group, right? Discrete is a finite reflection group. There's only finitely many elements. There's 6 elements here. Okay, but it's a reflection group, and these finite reflection groups are also called Coxeter groups. Okay. So an important structure theorem which circumvents this definition via normalizer mod centralizer is that W is generated by these simple reflections. Is that W is generated by simple reflections. Okay. There's a book by Humphreys which gives a nice proof of that. Okay, but any this one, sorry. So any element of the Weyl group can also be written as a called Weyl word. Okay. And we're gonna write it functionally. Okay, so basically right to left in terms of order. So for example, 2, 1 means S alpha 2, S alpha 1. You do S alpha 1 first. Okay, so 2 ways to write elements of S3. Okay, so as a permutation, notation. So we have identity 1, 2, 2, 3, 1, 3, 1, 2, 3, 1, 3, 2. So that's what we've used so far. And then vile word notation. I want to say vile word notation. Vile word notation. Identity 1. So really this means S alpha 1, right? 2. This one you could write in 2 different ways. Let's write this properly. 2, 1, 2, which is the same thing as 1, 2, 1. 1, 2, 2, 1. Okay. So there's some checking here to do, of course, right? But that's, everybody understand what I'm saying about the notation? Okay. You're composing very simple reflections. Okay. Okay, so jump the gun here with move this around.
This means that if the dimension is less than 5, it's an abelian, right?
Just a minute, please. Okay. If what's less than 5?
The dimension of the weight group.
Let's not talk about dimension here. We can talk about the size of the algorithm.
No, the dimension of the Lie group, like of the group inductor, because it's a subset of something that is not S5. I remember, if I remember correctly, S4, S3, and S2 are abelian.
S3 is definitely not a
It's the simplicity.
No. Careful. Yeah, you're talking about simplicity. Okay. So the walls alpha perp for alpha. So these divide H star R into Weil chambers. Okay. So a fact about the Weil group, again, I'm not going to show it. Probably don't have time. Is that W acts simply transitively on these. Okay, what does that mean? It means that, so simply means that if I pick any chamber and I ask which elements of the Weil group stabilize that chamber, it's just going to be the trivial elements. Okay, that's the simply part. Transitively means, consider the action of W on these chambers. It means that given any two, say this one and this one, there is an element in the Weil group that maps one to the other. Okay, you could get anywhere you want in this set of Weil chambers. So that means there's a bijection between a correspondence, right, between the elements of the Weil group and chambers. Namely, I pick one of them, say this one that I've called the fundamental one, and then I pick another one, and I'm going to label this one, this chamber, by the element, the unique element of the Weil group that sends me there. Okay, so these have the same size. The number of chambers is exactly the same as the size of the Weil group. Okay, and so this is like, if I take this as a fundamental one, then I've labeled it with 1 because that's the element. S alpha 1, the reflection through alpha 1 perp is what gets me over there. if I want to get over here, I have to compose 3 times. So S alpha 1, S alpha 2, S alpha 1 in that order, or do this one, S alpha 2, S alpha 1, S alpha 2 to get over here. Double check that this is what happens. Okay, so for this particular chamber to get you over here. Okay, little exercise. So you can see so if you have something inside in the interior of this Weyl chamber, so I'm talking about open Weyl chambers, then these orbits are I mean, you can get from anywhere to anywhere, right? These orbits start degenerating when you start picking a point on a wall of on one of these walls. Okay, because this is now going to have a non-trivial stabilizer, obviously, because the reflection, say in alpha 2 perp, right, it keeps it there. Okay, so here, whereas here, if I pick a point over here, the number of elements in that orbit, the W orbit through that point is going to be 6. Here on a wall, it's 3. I get an equilateral triangle. I get highly symmetric figures, right? Because this W is an orthogonal. Is an orthogonal, a subgroup of the orthogonal transformations. Okay, so like this distance here between a point that I am selecting, right, along an orbit, it's the same as the distance here, same as the distance here. Okay, we're working with orthogonal transformations, so these preserve distances. Okay. Okay, so we have a little bit of time left. I'll get to talking about this next topic a little bit. Okay, so Weyl orbits on weights. Okay, just to motivate this a little bit, because it's really, once you get used to what's happening, it really simplifies, reduces the complexity of what's happening. Okay, so what is the question motivating this section? So we're going to want to see the effect of these reflections in an efficient manner, right? As opposed to just using the definition of reflection every time, we want a nice calculus for doing this. So let's take the ith simple reflection. Let it act on a weight. Okay, so specifically this means a lambda 1 plus b lambda 2. So what is this? Okay, we want to be able to evaluate the effect, and then we could see the how these orbits look like. So I'm not going to use summation convention below. So let's just to be a little bit more clear. So let's let lambda be this weight that I'm going to write in the fundamental weight basis. And let's recall that alpha I is given in terms of the Cartal matrix. You could write it with respect to the fundamental weights. Okay, so now let's look at the effect of this reflection on this weight. And just write it out a bit. Okay, so this is the definition of what this reflection, this simple reflection does. And now let's write it out. Okay, so we have lambda minus lambda. I'm going to write out as, oops, this linear combination here. I'm going to pull the coefficients outside the pairing. So what I have is Rj, and then you have lambda j alpha I check alpha I. This is something nice. This was from the definition of fundamental weights. This is a delta ij. Okay. This is a summation over j, so I only get a non-trivial contribution when j is I. So what I'm getting is lambda minus Ri alpha I. We want to see the effect on these coefficients. So let's write this lambda out. Okay, so Rk lambda k minus Ri, I'll use this formula over here. Lambda k. Okay, so we have, let's just collect everything in terms of the lambda k basis. We have rk minus ri cik lambda k. Okay, so these coefficients, oh, I gotta move this stuff again. These are my new these are my new coefficients. Okay. So the new weights as rk tilde is the original rk minus ri cik. No summation on I. Okay, so note CII is 2. So the ith one gets flipped to its negative. This is actually going to give us a recipe. Okay, so let me just write out this recipe for SL3. And despite the complexity of the calculation above, the algorithm here is very simple. So what we have is this Cartan matrix, remember, in the SL3 case. And what we get is a recipe. So what is this going to do to the weight AB? So this is the first simple reflection, and this is going to send it to its negative by what we just said over here. From this guy over here, the effect on the second coefficient is I take the value of what's on that first coefficient over here, and I'm going to add it to that. Similar effect for the other one. Okay. So what we could do now is really generate these orbits very, very quickly. So sample W orbits, and I think I'll leave it up after. I'll close it after these examples. Let's start out with 1, 0. This was lambda 1, the highest weight of the standard representation. Notice that if I do S alpha 2, it's not going to do anything to this. Okay, so I had B is equal to 0. It doesn't do anything to that weight. That weight, yeah, it lives in the wall alpha 2 perp. So S alpha 2 is not going to do anything to it. So we're going to apply S alpha 1. Okay, so what is this going to do? Flips the coefficient over the first node to its negative, and then adds it. So 1 plus 0. So it becomes on the second coefficient. I'm going to apply S alpha 2, and so this flips what's on the second coefficient, and then I take this and add it to that, which is 0 for the first coefficient. And this is that orbit in the standard representation, right? This is lambda 1, this is minus lambda 1 plus lambda 2, and this is minus lambda 2. Let's do one more to end it off. So we start with the adjoint representation. We're going to apply the first one, first simple reflection. So flip the first coefficient, take what the value of that coefficient is, add it to here, so we get 2. Symmetrically, I do it to the other one. So you have 2 minus 1. Here, yeah, so I'm always going to apply it wherever I see a positive coefficient, I'm going to apply a reflection there. I'm not going to do it to -1 because that's going to backtrack me through the orbit. So we have this and that, and here I get this and that. And lastly, you get that. And those are exactly those 6 outer points in the adjoint representation. And you could compare what we just produced. Okay, this is exactly what's going on over here. We're looking at orbits. Yep.
So does mean we start at a point and we go at the same time both right and left?
Not necessarily in that order. It depends on well, actually from here, yeah. So this is alpha 2 perp, and this is alpha 1 perp, right? So the first application got you here and here. Okay, but then afterwards, I don't know the order here, but yeah, you could check the effect here. Okay, it's not necessarily just going around like that. Okay, yeah, so check what that is. Okay, so in this way, but of course we're not getting all the weights in the representation. We're missing in particular the 0 weight, as should be expected, right? Because this is an orthogonal transformation. We're starting out with a non-zero vector, so you're never going to produce the 0 vector. Right? So that's a different orbit. Okay. So yeah, we'll continue with this next time. We'll talk about the Weyl dimension formula. So given a representation AB, what is with highest weight AB, what is its dimension? There's a nice formula for that.